Hi friends, this is the fourth lecture in the lecture series for the preparation of GATE in mechanical engineering. Today we will be dealing with steady one-dimensional heat conduction. Okay, so in this case or in this lecture we will be dealing with different geometries through which steady one-dimensional heat conduction is occurring, such as plane wall, hollow cylinder, hollow sphere. Okay, and for all these cases what we are going to determine in all these cases is first one we will be determining the temperature profile. Okay, so second one we will be determining the temperature distribution that is occurring in this all these geometries, and this third one is the heat transfer rate that is occurring in all these cases, and the fourth one will be thermal resistance that is occurring. Okay, so these are the four questions that we are going to answer in this lecture for these three geometries. So before that, let's define the governing equation for the steady one-dimensional heat conduction. So the governing equation is Laplace equation. Laplace equation, which can be mathematically described as del square t is equal to 0. Please go through the previous lectures to get a better understanding in this equation. Okay, I mean the governing equation. So let's go through the first geometry, that is the plane wall. So let's suppose this is x direction and this is y direction. Consider a plane wall on this axis and which is having dimension L, which is having the width L, and let's suppose this is the temperature, this is the surface which is having temperature T1 and this surface is having temperature T2. I mean these points are having temperature T1 and T2, and suppose T1 is always greater than T2. For this case we can write this governing equation as del square T will be equal to 0. So this is the governing equation. So for this particular case we can translate this into Cartesian coordinate system as d square t by dx square will be equal to 0. So this is the governing equation. In order to find the temperature profile, we have to integrate this governing equation twice. For that, we are going to integrate this equation. dt by dx will be equal to a. This is the first integral. And further integrating again, we will be getting t is equal to ax plus b. So this is the temperature. So this is the temperature profile. We can see that this temperature profile is linear in nature. So the temperature here will be varying linearly from higher temperature T1 to lower temperature T2. So that's about the temperature profile. Then let's go to the temperature distribution. In the temperature distribution, in order to find the temperature distribution, we have to find the constants A and B in the temperature profile equation. For that we have to define the boundary condition. So first boundary condition is at x equal to 0, T will be equal to T1, and at x equal to L, which is the second boundary condition, T will be equal to T2. Applying these two boundary conditions into the temperature profile equation, we can find the temperature distribution as T minus T1 by T2 minus T1 will be equal to x by L. So this is the temperature distribution. Okay, so next we can find the heat transfer rate, okay, which is denoted by q dot, and this heat transfer rate can be determined as q dot is equal to q bar into AC. This q bar is the heat flux and AC is the area through which the heat conduction is happening or heat transfer is occurring. So this can be written as minus k dt by dx into AC. Okay, so in this case we can write this dt by dx as A, and this AC can be is the area. So by rearranging all these terms in this equation, we can find the governing equation for the heat transfer rate as minus q is equal to T1 minus T2 by L by KAC. Okay, so this is the heat transfer rate where Kc is the K is the thermal conductivity. Next one is the thermal resistance, which is denoted by the letter RTH. So to find this thermal resistance, let's suppose some resistance is there between two potentials V1 and V2. Resistance is having value R because suppose V1 is greater than V2. Suppose V1 is greater than V2, some current will always flow in this direction from V1 to V2. So in this case we can write from Ohm's law V1 minus V2 by R will be equal to I. Okay. Similarly, between two potentials, let's draw some thermal circuit between the potentials T1 and T2, and this resistance is having value RTH, which is the thermal resistance. So since suppose T1 is greater than T2, since T1 is greater than T2, some heat is flowing in this direction, which is Q dot. In the same manner as explained by Ohm's law, we can write T1 minus T2, which is the potential difference, divided by the resistance RTH will give the flow, that is nothing but the heat flow over here and the current over here. So comparing these two equations, that is Q for the Q dot, we can find Q dot is equal to delta T by RTH, which is equal to T1 minus T2 by L by KAC. Comparing these equations, we can write the RTH will be equal to L by K into AC. Okay, so this is the equation of thermal resistance. So that's it. Next we will be dealing with the second geometry, which is nothing but the hollow cylinder. Let's draw the hollow cylinder first. Suppose this is at R1, radius R1, and this is at radius R2, and this is the center line. Suppose this is the line through the radius R1 and R2. So let's suppose we are having temperature T1 over here and temperature T2 over at radius R2. In our case, T1 is greater than T2. Let's suppose T1 is greater than T2, and we know the governing equation as del square T is equal to 0. In the cylindrical coordinate system, we can write 1 by R square d by dr into R dt by dr will be equal to 0. So this is the governing equation. So let's move to the temperature profile. Okay, so this temperature profile can be determined by integrating the governing equation twice. For that we can write R dt by dr will be equal to A implies dt by dr is equal to A by R. Okay, next integrating again, we will be getting T is equal to A ln integrating again we are getting the temperature variation as T equal to A ln R plus B. Okay, so this is the temperature variation, and we can see that this is a logarithmic variation. So here what is happening is there is a logarithmic variation of temperature between these 2 points. Okay, so that's it. Next, let's go to the temperature distribution. To find the temperature distribution, as in the last case, we have to define the boundary condition as at R is equal to R1, we have temperature T is equal to T1, and at R is equal to R2, we have temperature T is equal to T2. Okay, so we can write the temperature profile by manipulating mathematically some works. We can write this as T minus T1 by T2 minus T1 will be equal to ln R minus ln R1 by ln R2 minus ln R1. So this is the temperature distribution for one-dimensional steady state heat conduction in hollow cylinder. So next we have heat transfer rate. Heat transfer rate, which is Q dot, and this Q dot or heat transfer rate is given by the equation Q dot is equal to Q bar into AC, which is nothing but K into dt by dr into AC, and this AC is the cross-sectional area, and we know that this AC is 2 pi r into L, and this K dt by dr is equal to K by R. Okay, so substituting these values into the equation, we can write this Q dot by some manipulation as Q dot will be equal to T1 minus T2 by ln R2 minus ln R1 by 2 pi KL. Okay, so this is the heat transfer rate through a hollow cylinder for one-dimensional steady-state heat conduction. So that's it. Next one is the thermal resistance. Thermal resistance RTH, and in the similar way that we determined earlier, we can define these RTH will be equal to delta T by Q dot. Further changing some values, we can write this RTH will be equal to ln R2 minus ln R1 by 2 pi KL. So that's it. That is the equation for thermal resistance. Okay, so these are the two cases. Now let's move to the next case, which is the next geometry, which is the hollow sphere. Okay, in this hollow sphere, let's do the hollow sphere first. This is the radius R1 and this is the radius R2. In this case, here suppose at R1 we are having temperature T1, at R2 we are having temperature T2. T1 is always greater than T2. So that's it. Let's go to the derivation equation first. It's nothing but for T is equal to 0. In this spherical coordinate system, we can write 1 by r square d by dr into r square dt by dr will be equal to 0. So this is the governing equation for a hollow sphere in the spherical coordinate system. So next we will be dealing with the temperature profile. For this temperature profile, we have to integrate the governing equation twice. So first integration will give r square dt by dr is equal to a, implies dt by dr will be equal to a by r square. So integrating again, we will be getting the equation for temperature, which is T is equal to minus A by R plus P. So this is the temperature profile for the hollow sphere in which steady one dimensional heat conduction is occurring, and this is hyperbolic variation. So in this case, that is for the hollow sphere, the temperature will vary hyperbolically. Temperature will be varying hyperbolically. Okay, this point T1 to this point T2. So that's it. Next, we will be dealing with the how the temperature distribution is there. To find the temperature distribution, we have to determine the constants A and B in the temperature profile equation. For that, we have to define the boundary conditions, that is at R is equal to R1, which is the first boundary condition, T will be equal to T1, and at R is equal to R2, T will be equal to T2. These are the two boundary conditions. Applying these boundary conditions to determine the constants A and B, then applying these constants into the temperature profile, we will be getting the temperature variation as T minus T1 by T2 minus T1 will be equal to 1 by R1 minus 1 by R by 1 by R2 minus 1 by R1. So this is the temperature distribution for hollow sphere. Next one is the heat transfer rate. Heat transfer rate, and this is Q dot is equal to Q bar into AC. So this can be written as minus K dt by dr into AC. That is, here dt by dr is A by R square, and this AC is 4 by R square. So for that, we can write this Q dot as Q dot will be equal to T1 minus T2 by R2 minus R1 by 4 pi K R1 R2. Okay, so this is the heat transfer rate equation for this spherical sphere. Next, the thermal resistance, that is RTH, can be determined by in a similar way as RTH will be equal to delta T by Q dot, which can be written as RTH will be equal to R2 minus R1 by 4 pi K R1 R2. So this is the equation for thermal resistance. At the end, we can define for all the cases as, suppose for all geometry, let's tabulate all these cases. First table geometry, second table is the temperature profile, and next third one is the temperature distribution, next heat transfer rate, next one is the thermal resistance RTS, and this temperature profile is the value of T, and this is T minus T1 by T2 minus T1. So for the geometry plane wall, we will be having temperature profile T equal to Ax plus B, as the temperature distribution will be X by L. The heat transfer will be Q dot is equal to T1 minus T2 by L by KAC. Here the thermal resistance RTH is equal to L by KAC. That is for the plane wall. Next, for the hollow cylinder, this temperature profile T is equal to A ln R plus B, and this is logarithmic, and this temperature distribution will be ln R2 minus ln R1, ln R minus ln R1 by ln R2 minus ln R1, and this Q dot will be T1 minus T2 by ln R2 minus ln R1 by 2 pi KL. So next the RTH will be ln R2 minus ln R1 by 2 pi KL. So that's for the hollow cylinder. Next, for the hollow sphere, the temperature profile will be T is equal to minus A by R plus B, that is hyperbolic. Hyperbolic. This temperature distribution will be 1 by R1 minus 1 by R by 1 by R2 minus 1 by R1, and this Q dot will be T1 minus T2 by R2 minus R1 by 4 by R1 R2 into K. So next one, the RTH will be R2 minus R1 by 4 by K R1 R2. So these are the equations. Learners, please note that everyone has to memorize this temperature profile distribution and heat transfer, and this last one, which is the thermal resistance. Thermal resistance. So we can find Q dot, and which will be used to find the E plus, that is Q dot by AC. This is heat flux, and this is Q dot, that is heat transfer rate. And also one equation is there, Q dot is equal to delta T by RTH, and RTH will be equal to delta T by Q dot. Okay.